In this video, I'm going to talk about logistic regression. And the example I'm going to use is for some department store data. And the department store has surveyed 100 of its customers, and this variable x1 measures their annual spending in thousands of dollars. And then this indicator variable, x2, indicates whether they have a credit card for the actual department store, a department store credit card. And then the outcome variable here, y, the dependent variable, the response variable, is an indication of whether the customer uses a coupon that they were sent in the mail. And 0 is if they did not use the coupon, and 1 is if they did use the coupon. And so the idea here is to see if either or both of these two predictor variables, spending and whether they have a store credit card, will help us predict whether they're more or less likely to use the coupon. So this type of model, or this type of data set, cannot be modeled using multiple linear regression because the response variable is not quantitative. Rather, it's what's called a binary response variable. It has just two possible values, 0 or 1, measuring whether an event happened or not. So in this case, the event is whether they used the coupon or not. One way to analyze this type of data is using something called a logistic regression model. And it has some things in common with linear regression and some things that are very different. One thing that's very different is the way it's estimated. And it turns out to be a lot more challenging to estimate than linear regression, which uses the method of least squares. The method of least squares doesn't work here. And so we rely on statistical software to estimate logistic regression models. Unfortunately, the version of XLStat that I have doesn't offer the logistic regression option. It would normally be in this menu, and we would be able to fit the model using XLStat. But unfortunately, we can't do that. So instead, I'm just going to report the results, and then we'll interpret the results, which is kind of the more important task at hand anyway. So the results, we're going to report them in a coefficients table over here. And so just like with linear regression, we get estimated parameters. So we get an intercept, minus 2.146, and then a parameter that goes with x1, 0.342, and a parameter that goes with x2, 1.099. And we can use these estimates to come up with what I'm going to call just now a fitted value. So it's not actually a predicted response, which it would be in linear regression because the model's a little bit different, but we'll talk about that in a second. For now, let's just use the equation as it's given to us and figure out what minus 2.146 plus 0.342 times x1 plus 1.099 times x2, what that comes to for each of our sample observations. So it's minus 0.2635 for the first one, 0.0525 for the second one, and so on, all the way down. What we have to do to these numbers is we have to transform them so that they become meaningful in the context of the logistic regression model. And the way that we do that is to apply this transformation here. We exponentiate the number, so that's what exp of d2 means. And to exponentiate a number means to have the number e raised to the power of in this case, minus 0.2635. And then we divide that by 1 plus EXP of the number. Okay, so that's the transformation that we're using here. And what this transformation does is it turns this number into a number that we can interpret as a probability. So it's a number that is bounded between 0 and 1, and it represents the probability that we're modeling that tells us how likely it is that a customer with these particular characteristics for X1 and X2, how likely it is that they'll use the coupon based on the sample data. So for this customer, they got an estimated probability of 0.4345. So that's the probability that this type of customer will use the coupon based on the sample data. This customer is a little more likely to use their coupon. They have a probability of 0.5131. Let's find a couple of extremes. This customer is not at all likely to use the coupon. Let's find one that's quite high. None of them are super high, are they? Let's find one that's a little higher than the rest. Well, this one's kind of getting up there, 0.5790. Maybe I can find one. Oh, there's a big one, 0.6874. So what we want to do is analyze that equation that we had given by these numbers to see what it is about X1 and X2 that's giving us big numbers. Oh, there's a really big one. What is it about this customer that's giving us a big number here versus this number right next to it is it's kind of on the low side. So the numbers we're looking at, this is X1, this is X2. So if we compare these two examples, this customer has a much bigger value of X1 than this one. And they also have one of the store credit cards. And they have a much bigger probability of using the coupon than this customer. Okay, so that actually fits with these numbers here. So the fact that this estimate is a positive number and it's multiplying spending, that's going to result in an increased probability of using the coupon. And similarly, this is a positive number, and customers that have a store credit card will have 1.099 added onto their fitted value, whereas customers that don't will not have that 1.099 added on. So again, having a department store credit card increases the probability of using the coupon. It's not quite as simple as in linear regression, though, where we had an additive effect that we could see, okay, this is how much Y is going to change when spending increases by 1. Because the impact is on this fitted value here. It's not directly on this probability here. So the way that we get around that is to transform this estimate. We do that by exponentiating the number, taking e to the power of 0.342 and e to the power of 1.099. And we get these results here. And this represents the change in the odds of increasing spending or having a credit card. So in particular, the odds of a customer using their coupon increases by 1.4078 times for each $1,000 increase in spending, assuming that card is fixed. Okay, so essentially we're comparing two different types of customer. Let's say they both have a credit card, a store credit card, One has an annual spending of $3,000. The other one has an annual spending of $2,000. The one with the annual spending of $3,000 will have an increased odds of using the coupon of 1.4078 times over the other customer that had only $2,000 spending. What do I mean when I say odds? Odds is the ratio of the probability of using the coupon divided by 1 minus the probability of using the coupon. So that's how to interpret the regression parameters. Let's interpret this one as well, just so we're clear on what it means. So this is for the card variable. So this is comparing customers with a credit card to customers without a store credit card, given that they both have the same amount of spending. So let's pick two hypothetical customers. One has a spending of $2,000 and has a store credit card. The other one has a spending of $2,000 but doesn't have a store credit card. The one with the store credit card will have an odds of using the coupon that are 3.0012 times higher than the odds of the other customer using their coupon. And again, the odds means the probability of using the coupon divided by 1 minus the probability of using the coupon. Okay, so that's how to interpret the parameters in a logistic regression model. It's a bit of a mind, you got to really think it through. Okay, we can also think about testing the variables. So a hypothesis test for each variable in the model. We can do an overall test, and that uses, instead of an analysis of variance table, with logistic regression, we have an analysis of deviance table. And the top row here for the regression, it's not an F statistic here, it's a chi-squared statistic. We can look at the p-value associated with the chi-squared statistic to see if it's significant. And if it's less than our usual significance level of 0.05, we reject the null hypothesis, which says that the model is no better than flipping a coin. And in this case, we reject that possibility and conclude that there is value in this model, that there is a relationship between whether someone uses a coupon or not and how much they spend per year and whether they have a credit card or not. And then individual tests for each of the variables, we do those in the same table, and they have their own chi-squared statistics and their own p-values. And again, we're looking for values less than a significance level of usually 0.05 here, and in this case they're both significant, so both variables are having an impact on whether someone uses their coupon. Okay, the final thing I want to talk about is how might this particular analysis be used in practice. So what we can do is we can figure out the probabilities of using the coupon for different types of customer. So for example, someone who spends $1,000 a year and doesn't have a department store credit card. Someone who spends $2,000 a year doesn't have a department store credit card, and so on. So we go all the way up to $7,000, and unsurprisingly, we're keeping card fixed with customers that do not have a credit card. That's all these ones here. All we're doing is increasing the spending, and we see the probabilities increasing. And once they get to a particular threshold, those are the customers we want to target with our coupon because they're more likely to use it. So let's say if the threshold was 0.4, then we would target customers with spending of at least $6,000 a year. We might include this one as well. It's pretty close to 0.4. So maybe target customers who spend $5,000 or more. These are the ones without the credit card. Customers with the credit card, these should all be ones. There we go. That's better. So these are customers with the credit card, with the department store credit card. Again, we're just increasing spending by $1,000 each time and calculating the probabilities. So this time, because they have the department store credit card, they're more likely to use the coupon in general. And for this subset of customers, we're going to target anyone with spending of $2,000 or higher. These are the ones with the probability at least 0.4. So that's an example of how a logistic regression model like this might be used. Okay, so that's a brief introduction to interpreting logistic regression